So we come here now to the core shell model, and this is a model of how your body regulates heat, and it has two parts to it. It has the core, which is what is regulated. That is where your heat is generated, and it is the amount of heat that you generate that is generally regulated. So when you're cold, you're going to end up trying to create more heat. When you're hot, then you try and lower your heat production and get rid of the excess. And so that is the M in the middle. The plus M is the heat due to your metabolism. And then the core will have a temperature denoted Tc. And then on the outside of that, you have the periphery, and this is the skin and the subcutaneous fat, and this is not regulated and it's not held at a constant temperature. The temperature of the periphery will be a gradient from Tc on the inside all the way out to Ts, which is sort of your periphery, the temperature of the skin. And then surrounding that obviously is the atmospheric temperature, Ta, and this can either gain heat through radiation or conduction or convection, or lose heat either by those ways or as well by evaporation. So heat flow in the core shell model, we will summarize here. Heat flows between the core to the skin, driven by the temperature gradient. The larger the temperature gradient, the faster it's going to travel. So with Ts to Tc. And varying the cutaneous blood flow can greatly modify the effective thermal conductivity of the periphery. So you have this gradient of heat. Generally, if you're in a cold environment, your Tc is going to be higher than your Ts, and so you have a gradient of heat that's going to leave. But the speed that that heat leaves is going to depend on the effective thermal conductivity of the periphery, and that changes depending on what kind of circulation you have there. Generally, conductive will move slower than this forced convection we have, and so the more that the blood flows through the periphery, the faster, the larger this thermal conductivity is, and the quicker you will lose heat. Heat flows between the skin and the environment, driven by the temperature gradient that is between the atmospheric temperature and the skin temperature. So if your skin temperature is similar to the environment, there won't be a lot of heat loss. But then if there's a large amount of difference between the skin and the environment, you're going to lose a lot of heat, and vice versa. If it's very hot outside and your skin isn't so hot, heat will flow into the skin very rapidly. And this core shell model we talk about has limits, and these limits are that not all parts of the core are at the same temperature. The body tries to keep the core at the same temperature, but there are areas that are slightly hotter than others, as we see when it comes to measuring them. And also the shell is not fixed, or the core is not fixed, I should say. The core will expand and contract as the body sort of modulates how to maintain the thermal conductivity or change the effective thermal conductivity of the shell, and so it expands and contracts. And so this is shown here. In the warm environment, your core is very large as blood is pumped to many parts of the extremity, and your whole core temperature is kept at 37, and this includes a lot of the skeletal muscle. But then in the cold environment, your blood flow is pulled in, your core shrinks, and the shell becomes a larger insulating layer, so that the loss of heat from your core is prevented by altering then not just the thermal conductivity of the shell, but the general size of it. And so here we come to sites of temperature measurement. and we'll talk about 3, oral, under the tongue, and then you have rectal, and this typically is about 0.6 degrees higher than under the tongue, and so this shows already how you can have fluctuations in the different sites of measurement, which shows that your core is not totally fixed. Tympanic measurement then, putting a sensor in the ear. This usually detects infrared, and it's generally not only the easiest but the one that's used most in the clinic these days, because it directly approximates the temperature of the brain, where it is probably one of the most places to look at it. So here shows the differences of measuring temperatures of the body, oral and rectal. You can see that the rectal temperature measurements tend to be slightly higher than the oral measurements, even if you're measuring the same thing. So hard exercise rectally will be between 38.5 and 40 degrees C, or here orally it will be about 38. And the normal range is fairly similar, but again, rectal just slightly higher. Remember that your body has a diurnal rhythm. When you sleep, your body temperature is at its least, and that's probably because you're not producing as much energy as normally, and your thermoregulatory systems aren't working quite so hard. And then when you're much more metabolically active during the day, your core temperature is about 1 degree higher.